Today, in my lecture, I would like to move on from the area of control to the area of structural health monitoring. And one of the main efforts that we've been working on in recent times is smart sensors or wireless sensors. And I'll define what we mean by a smart sensor in a little bit. So the outline of the presentation is, first, I'll provide some background and motivation, and then to better understand why we're looking at wireless sensors, I'll describe some traditional structural health monitoring sensors. And then we'll move into the enabling wireless sensor technology, looking at hardware and software and algorithmic issues. And then I'll talk about some full-scale implementations, which is the proof of the approaches, and then we'll look at future directions and draw some conclusions. So why do we monitor civil infrastructure? The holy grail of structural health monitoring is to detect and localize damage. In the United States, in Europe, much of our infrastructure was put in place after World War II. And so the intended design life was on the order of 50 years or so. So much of our infrastructure is approaching, if not surpassing, its intended design life. And as a result, many of our structures have corrosion. They have fatigue cracks. This was in the Bay Bridge, where from one inspection there was no crack, to the next inspection the crack had already grown to critical and fractured the element in this I-bar. This is a bridge in Korea that's collapsed, and this is the I-35 collapse in Minnesota. As a matter of fact, if we look at this chart, this is from the U.S. Department of Transportation. The system expansion in 1997 was $21.5 billion. The rehabilitation was $23 billion, but if you look at 2006, while we've had growth in both figures, the growth in system rehabilitation is substantially larger than that in system expansion. But it's not just old infrastructure. This is a list of the failures of bridges in China in the last 3 years. I got this slide from Professor Yozo Fujino. And so it's the area of structural health monitoring is important, especially in economies that are rapidly developing, such as we see in China. But structural health monitoring is not only for damage detection. There are many more uses for it. As a matter of fact, many of the new structures that have monitoring systems on them, there's nothing wrong with them. They're brand new. And so unless there's a problem with infant mortality where you have some design problems, structural health monitoring is not of use. But we can use structural health monitoring for understanding and tracking the construction process. I'll show some examples of this. We can validate structural designs. I told you about the Burj Khalifa building, the tallest building in the world. SOM put sensors on there because they wanted to understand what they actually built. I mean, there was what was tested in the tunnel, wind tunnel. There was what was designed on the drawing board. There was what their computer models told them. But what did they actually build? How did this structure actually behave? So to understand the structural designs and characterize performance. What are the real loads on the structure as compared to what were expected? If the loads are larger than expected, then maybe retrofit measures have to be taken right away. If the loads are smaller, then in future designs we can have more economic performance. To assist with building and bridge maintenance, maintaining our structures, we have a particular project I'll discuss later on the maintenance and retrofit of railroad bridges. We're working with CN Railroad on that. And then, of course, to detect and localize damage. This is one of the important issues, to increase public safety, to reduce cost and downtime whenever these damage scenarios are found, and also to assist with emergency response. Toward the end, I'll talk a little bit about this, but the Internet of Things is on its way, where everything will be interconnected, and so a lot of the challenge will be dealing with the data, how to optimize it, how to be more effective. Now let me just give you a few examples. I like this particular example. It came from James Brown John, who was at Sheffield University at the time. It's a building, 280-meter tall building in Singapore, and so they did quite a variety of testing. Frequency measurements in 94, 95. They did monitoring since 96. They originally focused on wind data, but then they moved to this building being a super sensor for earthquake monitoring, when the building was much more sensitive than any instruments. Had dual GPS until 2005, and now it reverts to like a seismometer array. So this is an example where this building was being monitored during the construction process. And what we have here, this is the number of stories, and this is the period in seconds. And so what you see is that as the construction progresses, the building gets taller, it gets more flexible, the periods get longer. But what we see is a very stable behavior. If we would have seen any variations in this progression, then it would have been an indication that maybe there was a problem in the construction process itself. In the permanent monitoring, this shows some of the instrumentation, including an anemometer, GPS, a data logger, force balance accelerometers in the basement and on the roof level. And what you see here is a typical earthquake record that was recorded from this building. It's the aftershock of the Bengkulu subduction zone event in 2000. And in here you can see it triggered significant second mode response. You can see the second and the first mode, but significant second and even higher mode response here. And if you look at the design, you could create a design spectrum from all these events, so you've got real data to understand that particular site as it compared to what was expected for that particular site. So here's an array event. This is normalized to 1% damping, and so you can see that we can understand the structure itself, we can understand the loading on that structure as it was built. Now, one of the key things in the design of tall buildings is damping. We talked a little bit about damping yesterday, and I said there is no such thing as a viscous damper, and as a matter of fact, for tall buildings, we need to know what is the approximate damping in the structure. Is it 1%? Is it 2%? And so one of my colleagues at Notre Dame, Hassan Karim, working with his former student, Tracy Kajewski, they partnered with Skidmore, Owens, and Merrill, and they developed what's called Windy City. They had 4 tall buildings, 3 of them in Chicago, and one of them in 4 buildings in Chicago and 1 in Korea. And so they found that the damping, of course, it changes with time, and it's different from building to building. So this project, unfortunately, the data is not completely open, because if you're a building owner, you don't want people to know too much about your building for fear that you'll be liable. But if you're interested, more information can be found on their website. This was an interesting effort. This is some results from Bill Iwan at Caltech. The Millikan Library is one of the most studied buildings. They've done system identification since very early on. And this was in 2002. Bill Iwan, he partnered with, I forget the manufacturer of the Digitech, there we go. He partnered with Digitech to develop this computer interface so that online you could see the performance of the Millikan Library. And here are some results for this Millikan Library from the data that was collected by their system. And I thought there were some quite interesting behaviors. First of all, this is a 10-story building. And you would expect that in a 10-story building that the shear action would dominate. You wouldn't expect to see too much bending action out of this system. And so what I want to show you here, the total data. The data is given in this line over here. This is the first east-west mode. And it's comprised of a number of components. First of all, this is the rigid body rotation of the building on its foundation. This blue line is the shear of the core in the frame, and then the yellow line is the bending of the core. So in contrast to what we typically assume for the behavior of a 10-story building, which is dominated by shear, you had a combination of bending, shear, and rigid body rotation that were all needed to understand how that building responds.
That's followed in torsion, right?
Pardon?
That's followed in torsion.
In this particular case, this is just pure bending. This is just pure bending. This is the east-west first mode. I'm sorry?
The rigid body motion.
The rigid body motion was just, if I'm here, it's just rocking on its foundation. So it's a pure rocking behavior. So there certainly could be torsion, but this is a rectangular building, and so there's no noticeable torsion there. So it's the combination of just rocking on the foundation. That's the rigid body motion because of the flexibility of the soil. We usually neglect that. There's the shear behavior that we talked about yesterday, and then there's the bending behavior, which usually we don't think dominates until you get about above 20 stories. So the example here shows that it's important to understand the real behavior of structures, especially if you wanted to do a seismic retrofit of this and you didn't understand that bending was a significant part of the response, then your seismic retrofit approaches, they may be compromised, just as an example. This was some work by Yozo Fujino at the University of Tokyo. That's building number 11. That's where his office used to be. And what they did, this is just ambient vibration. And so what they wanted to do was to look at the effectiveness of the retrofit strategies. And so looking at the RMS response due to a 0.1 gal excitation, you can see that this was the unretrofitted structure, and this is the blue is the retrofitted structure. So this doesn't tell you that the seismic response control system is effective because the levels of excitation are too small. But it's the first step to try and understand the effect of those retrofit measures. So you can see here, these are the braces that were put in to stiffen the structure. So indeed, there was a stiffness increase in the structure. This is also from Professor Fujino. He's a Renaissance man. On the left is his painting of the Yokohama Bay Bridge. Each year, this is from 2004, each year he sends out a New Year's card that has a painting of some bridge throughout the world. And so they've studied the Yokohama Bay Bridge. They had had a monitoring system on there probably for 15, maybe 20 years now, because this data is a little older. And so what they wanted to do was to understand the real performance. So 80 sensors. At this time it was measured for more than 15 years and 10 earthquakes. Now, based on the data that they had, both the ambient vibration and the seismic data, they used the ERA method, system realization method developed by Zhuang and Papa. And here's what they found. That this, if we look here, this is what was assumed in the design, that the bridge deck would slip on the bridge piers, that the bearing would allow it to be free. And so in this February 1990 earthquake, indeed the bridge behaved as they expected, as it was designed. But if you look at this 1992 earthquake, you can see that the slipping didn't occur at the bearing, so the piers, those two piers, because there was no slip, were loaded much more heavily than they would have been otherwise. And down here you have a stick on the one end and a slip on the other end. So if you wish to retrofit this bridge, this is one of the critical modes of failure, the longitudinal response of the structure. It's not the lateral response of the structure, the longitudinal response of the structure. And it's important to understand how what the real behavior of the bridge is so that you can design appropriate measures. This is in Hong Kong, the Lantau fixed crossing. And there are three signature bridges. There's the Qingkao Bridge, there's the Qingma Bridge, and the Kapsui-Mun Bridge. And I just focus on the Qingma Bridge for a second. There are 300 sensors here. I'll just tell you now, I'm going to say it again later, but the installation was incredibly expensive. The average cost per sensor channel was about $27,000. So 300 sensors, data acquisition, cabling network, $7.8 million for the entire system. But they did measurement in 4 phases. First was the freestanding tower. Second was the tower cable system, and then the tower cable system with the deck going in place, and then the completed bridge. So I've shown you just a few examples. In Asia, nearly all of the bridges, all of the signature bridges will have a structural health monitoring system. As a matter of fact, in China, they're developing a code right at this minute, it will soon be published, that will require all bridges over a certain length and a certain class to have monitoring systems. And they'll have to go back and retrofit the bridges that don't have the monitoring systems already employed. So what's the current capabilities that we have for these structural health monitoring systems? We can do real-time data collection and presentation. We can do data storage. We can look at the statistics and compare with the baseline, and then if there's some anomaly, we can flag that. We can have warnings whenever we see strange behavior. However, the data is overwhelming. There's more data than can be dealt with. Sensor defects and premature failures. The typical bridge has a design lifeline of 100 years these days, these long span bridges. How long do you think a sensor lasts on a bridge? If you're 5 years, you'd be lucky. Some of the wired systems may last a little longer, some of the fiber optic sensors may last a little longer, but they're nowhere near the design life of the bridge. So sensor failure, premature failures of the thermometers, optical fiber, electrical resistant gauges, etc. Overall system failure. It's a PC that's running all of this. How long does your PC last? 3 years, 4 years? If you get 5 years out of it, it's probably running really slow. So there's a lot of maintenance associated with this. We still don't know how to really effectively use or conduct real-time damage assessment. I'll show you some of the algorithms that we've developed today, but this is an open issue, and it depends on the type of structure that you're interested in. General safety and health assessment, in addition to damage identification, and then the overall cost of the system. Now this is just a few examples. The Qingma Bridge, the Sutong Bridge, Stonecutters Bridge, Qingdao Bridge. And if you look here, the cost, the least expensive, is about $6,000 per channel. A lot of the cost is associated with cabling. All of the cables have to be put in conduit, and so the installation costs are substantial. Now, I show these bridges in China, but the costs in the United States are comparable. I'm not sure about in Italy, but in the U.S., as an example, the Bill Emerson Bridge over the Mississippi River near Cape Girardeau, the average cost of the 86 accelerometers installed there was $15,000. So $15,000 per channel. So our work has been directed towards wireless sensors. Now, wireless sensors are a whole new beast. Wireless sensors have the promise of being low cost, on the order of hundreds of dollars per channel. They have the promise of ease of installation, and they have the promise of accurate data. But realizing that promise is not trivial. And now these are just a few of the facts that if we look at how computer technologies are being driven. If any of you have heard of the new iPhone 5S, it's got an A7 chip in it from Apple, and it's about twice as fast as the iPhone 5. It's got its own graphic processor. It even has a separate chip to monitor the sensors that are on board so that it doesn't have to load down the microprocessor. An amazing thing. And the thing that's driving it is that we can make the cost of these devices, of the silicon chips, Less and less. So whereas in 1985 I was a graduate student at the University of Illinois, and we had the computer, an IBM 4381. And when they got it in, I played racquetball with one of the computer technicians. And so he let me have the entire computer, all 48 megabytes of this central computer for the University of Illinois. So we were in the cray times when it was hundreds of thousands of dollars to get, this is 1 million instructions per second. And we're down now where it's less than $1. Where computing is done, I mean, each of you likely has multiple microprocessors with you today, whether it's in your cell phone, whether it's in, I have a whole bunch on right now. There's probably a microprocessor in each of these microphones that I have on. There's a microprocessor here, there's a microprocessor on my laptop, there's a bunch of them in my mobile phone. And so, whereas in the 1940s, 50s, and 60s there were multiple people per computer, we're down to the case where we have multiple computers per person. And so the exciting thing there for engineers is that we can stream data to and from the physical world. Networking also plays an important part. So if you have data but you're not connected to anything, it's really of a lot less value. So some of the first computers in the 40s, it wasn't until the 90s that we got the internet. And now in 2010, we're moving to cyber physical systems. That is, that it's particularly appropriate for this conference because a cyber physical system is one that not only can sense its environment, interact with other sensors, but then it can execute control to change the environment. So what's the vision of the future? Vast networks of sensors installed in the urban environment that can serve as the eyes and the ears and the first line of defense against various vulnerabilities. Different types of sensors are envisioned, each reporting information that provides insight to the status of critical infrastructure in real time. And our view is that wireless smart sensors, because of their low cost and their modularity, will form a fundamental building block for realizing this vision. Now, what are smart sensors? Well, a wireless smart sensor, as it's commonly viewed today, has onboard computing and sensing capabilities. It's wireless, inexpensive, small, and battery-powered, easy to deploy and maintain, and it's ideal for what we call campaign monitoring, going out, putting the sensors on the structure, measuring the response, and then taking that data home. Now, before 1999, there was if you wanted to have wireless sensors, you had to make your own. Just about the time you got one made, that student graduated and you almost had to start over. So in the late 1990s, there was the Smart Dust project, the DARPA NEST, Network of Embedded Sensing Technology, and it put a lot of money into this idea of developing these small sensors. Their goal was to develop a sensor with all these capabilities, a smart sensor in 1 cubic millimeter in size. That was never realized, but they did get quite small, as you can see here. This is one of the early prototypes, and these are a bunch of other versions of different companies, different researchers, and some of them were available commercially, some of them were just in the laboratory. So, for example, the guys at Berkeley developed the Rene and Mica platform, and they licensed it to Crossbow. So all of a sudden, instead of having to make your own wireless sensors, you could go out and buy them, and you could focus on the research, engineering research, as opposed to having to get everything connected together. Now, full-scale implementations, there's a few selected ones here, and what you see is that first full-scale implementations were just 10 years ago. This was by Jerry Lynch, who's now at Michigan. This was when he was at Stanford working with Chuck Farrar at Los Alamos National Laboratories. And they installed 7 nodes, which each had 2 accelerometers in there, and it was a short-term deployment. And then there were a number after that. Now, I'm going to show you a little bit more about this effort of the Golden Gate Bridge. There's a fellow, Greg Fenves, he's the inventor of OpenSeas, the finite element code that Berkeley has, and he was working with David Culler. David Culler was the author of TinyOS. It's the operating system that runs on these wireless systems. So they partnered together to deploy the largest wireless sensor network for monitoring civil infrastructure to date, largest in the world. They had 128 accelerometers on there and 64 temperature sensors. Now, let's look at that in more detail. It was really a great achievement. However, this is just a picture of the Golden Gate Bridge so you can recall the idea of scale. So they had 51 nodes on the deck. They had the other nodes here on the tower. This is one of the installations. Here's where the wireless sensor was. They had a large battery supply, 6-volt Lannard batteries times 4. This was a patch antenna connecting it. So this was a single node in which they had 2 accelerometers in there. Now, the challenge was that it required 12 hours to collect 80 seconds of data. What if you wanted to collect 5 minutes of data or 10 minutes of data? It could take days. So no wonder they needed these large batteries. The problem that they had was they treated this wireless sensor network as though it were a wired network. They tried to emulate the wired network. But you can't do that with wireless sensors. You have to look at what their capabilities are, and what I would advocate, I'll show you, is that you have to use the in-network processing to try and understand what data is important and what data is not important. If data is not important, you don't have to send it back to the base station. You don't have to send it back to the bridge owner. Now, there's been a number of other more recent efforts. In particular, Jerry Lynch has a nice deployment of 30 sensors on the new Cartines Bridge. It's a long-term deployment, and Jerry is one of the other leaders in the field of wireless sensor monitoring. But I'd like you to look at this. These wireless sensors were first available commercially in about 1999. But despite that availability, the vision of having ubiquitous sensing, having many low-cost sensors easily deployed on a structure, has yet to be realized. And so what's been lacking? Well, the hardware hasn't really met the needs of structural engineers. The software is extremely difficult to work with, and so to write new algorithms can be more than challenging. And then there's been few full-scale implementations that really demonstrate the potential of this technology. So we've made some significant advances in all of these areas, and that's what I'd like to tell you about this morning. So I'll first focus on the hardware. In about 2004 or 5, there was a fellow, Ralph Kling. He was one of the graduates from our department. He worked at the Intel Research Laboratories. And he visited and he told us about the iMote that they were developing. I want you to look, this is the Mica Z from Berkeley, and it had a clock speed of 8 megahertz. I mean, your phones have gigahertz clock speeds now. They were trying to get low power, long battery life in these systems. If you look at the amount of memory it had, 4 kilobytes of memory. How much in the way of calculations can you do with 4 kilobytes of memory? And even the non-volatile memory for storing data, they had 100 or 512K of flash, so a half a megabyte. Very, very low capabilities. And so when we saw this iMote, it came out, it had an X-scale processor. Same thing that if you remember this HP iPAC personal digital assistant, they also made phones. The X-scale processor was what was found in that phone, and it had a fast CPU. You could in software select the speed of the CPU from 13 to 400 megahertz. It had lots of memory for storing data, 32 megabytes. It had lots of RAM for writing complex calculations. And they had a sensor board that came with it. It had a triaxial accelerometer on it, and it had temperature, humidity, and light. So we were really, really excited about this. We thought that this was the answer to all of our prayers, that we could just take this sensor, take this wireless node, and that we'd be off and running. But it wasn't that simple. There were, I think we bought 14 of these nodes. And of course, the first thing you do with any sensor is you want to calibrate it. We put it on our shaking table. We started shaking it. We got 14 different signals. Not a one of them was the same. You might have expected the amplitude to be different, but you wouldn't have expected them to be completely different. Well, what was some of the problems? I said it had a light sensor temperature and then a triaxial accelerometer. Limitations: low ADC resolution, inaccurate sampling rate. So you would set the sampling rate at 100 hertz, and it'd be 100 hertz plus or minus 10%. So you can see here, this was for the sensors that we had, ranged from the 560 was the nominal sampling rate, 530 all the way up to 610 was what we got. In addition, the sampling rate wasn't constant with time, so it varied with time. So how can you use this for real structural analysis, for real investigation of the behavior of structures when your sensor isn't behaving as you expected? In addition, they said they had anti-aliasing filters on there. I don't know if you guys have dealt with aliasing before, but they had a single pole anti-aliasing filter at about 50 hertz, so the roll-off was very, very, very slow. But I thought I'd just show you here what aliasing is, because this was part of the problem that we had to deal with. This is a 48 hertz signal, and if you sample that at 50 hertz, you get the red dots. So it appears from the data that this is a 2 hertz signal, and this is the phenomenon of aliasing. So in terms of what that can do to our structure, imagine that this was your the spectrum, the real spectrum of the response of your structure. Now, in real structures, you don't have a 3 degree of freedom system where you can say, I've got 3 modes here. There's usually a continuous spectrum of modes. You'll have them wherever you choose to stop. This is the response I'm interested in. There will be frequencies above that. And so this is an example where you set the sampling rate here. You have these 3 modes. This is the Nyquist frequency. And so what happens is any energy above the Nyquist frequency gets folded back into the lower spectrum. And this would be the measured response if you didn't have anti-aliasing filters. So it would look like you had 3 modes in your baseband frequency, but one of them was due strictly to the digital signal processing, bad digital signal processing. So once you've sampled your data, you can't get rid of aliasing. What one has to do is, before you sample the data, you have to apply an analog filter which wipes out the higher frequency response. Now when you sample the data, you can get clean signals that can be used for your analyses. So we discarded this sensor board from Intel, and one of my students, Jennifer Rice, designed this sensor board. This sensor board also has a triaxial accelerometer. It has a quick filter chip with a digital signal processor. It allows us to have user-selectable sampling rate, user-selectable anti-aliasing filters. And it had a sensitivity of about 0.3 milligis. This was the one that Vincenzo showed yesterday that was using in L'Aquila. But we found that this was great for the response of structures in the 20, 30 milligi range. But if you have the low amplitude vibrations such as Vincenzo was showing yesterday, or we were interested in monitoring the Guangzhou new TV tower. It had a natural period of 10 seconds. In a typhoon, the maximum amplitude of the accelerations were around 20 milligis. So very, very low level, low frequency and low amplitude acceleration. So we developed this sensor board in which you could get resolution down to 0.05 milligis. We also developed another number of other boards. This one, a data acquisition board, which was used for wireless anemometer. Now, all of these were developed by civil engineers, students that had a civil engineering background. We felt that that was very important. They studied the electrical engineering, the computer science, and then they developed these electronics that could meet our needs, because we found that it was almost impossible to get the electrical engineers to understand the true needs that we had for our problems. Now, this is just a simple verification of this high sensitivity accelerometer. You've got a 5 kilogram mass on here. The first natural frequency was at 0.14 hertz, so very low frequency behavior. And what you see here, this is the time history of the response. This is in the frequency domain, so you can better see what we were trying to understand. The original sensor board with the 0.3 millig response was not sensitive enough at the low frequency to capture this first natural frequency of this beam type structure. So what you see is that the high sensitivity accelerometers had much lower noise floor, and they were able to capture that low frequency behavior, whereas the original system that we designed, the original boards that we designed, they weren't able to. So why don't we just all use this high sensitivity accelerometer? It's because it costs about 2 to 3 times as much as the standard accelerometer. So one has to have a mix of these things. We also developed some strain sensor boards for the IMO2 platform. And this was a really neat device. It was a magnetic strain checker. You could go up, you put it on your structure, you clamp down the lever, and you're measuring strain response. This shows some of the results for the strain sensor board that we developed versus a wired sensor gauge. This is in the high amplitude response, this is in the low amplitude response. And what's interesting is the wireless sensor got better low amplitude response than the wired sensor. How is that? Well, if you look, the wireless sensor had a lower cutoff frequency. It had a 30 hertz cutoff frequency, whereas the wired sensor had a slower roll-off. So it's the difference in between these two curves at this higher frequency that results in this additional noise that's seen in the signal. So, in addition, we've put these sensors in boxes. We've attached solar panels to them. You can see how it's done. It's got a rechargeable battery. This is the wireless sensor and the sensor board. The antenna goes to the solar panel. That's how the antenna is connected to the board. And we used high-strength magnets to hold the sensors onto the structure. We found that that worked better than gluing or any of the other approaches, and even used these magnets for attaching the solar panel. So what I want to contrast this to is the deployment at Berkeley, which was indeed a very impressive deployment, but they didn't take into account a number of the practical issues. And so what we have here is a very nicely packaged system that potentially can be deployed for structural health monitoring. Now, one of the things, you might imagine that the radio performance of these sensors, it would be easy to understand. I mean, we don't think much about the radio performance of your mobile phone. But the difference here is that these are relatively low power devices. And so we wanted to understand the performance of this antenna and the radio on the board. And so we did a number of anechoic chamber tests. One of the reasons was that the first student that worked on this, Tomonori Nagayama, he took the sensors out and he put them in the grass in the lawn outside of Newmark Laboratory, and then he walked back to see how far he could receive the signal. It was about 30 feet. Not very good at all. Well, we found out later, because we hadn't done anything in this, that grass, leaves, the water in the grass, the water in the leaves blocks the signal. Plus you have ground effects, the radio waves bouncing off of the ground. And so we found that understanding the performance of the antenna was very important. This is the copolarization and the cross-polarization plots for the antenna. So basically these antennas radiate like a donut. And if you want two antennas to communicate with each other, if they're perpendicular, they're not going to communicate. You need to have your antenna parallel, was one of the lessons that we learned. And by doing this, we found, this is a picture of one of the cornfields in Illinois. You can see it's extremely flat. We don't have mountains, we don't have oceans, we don't even have trees. And so but it's very good for testing radio communication. And we found that we could go up to about 1,200 feet, which is 300 plus meters in ideal conditions. Moreover, we learned that there's a lot of other communication on this 2.4 gigahertz bandwidth. So you had to understand, if you wanted to use the wireless sensors, we had to learn a lot about the radio performance, about other devices. This was the internet in our building. This was the iMote 2. So if we tried to use a band in this 11 to 13, channels 11 to 13, we would have gotten really bad performance, as shown here. So all of these types of issues with regard to the radio had to be understood to make use of the hardware. This just shows the attenuation of the signal for steel, reinforced concrete, masonry units. And so in general, steel structures are not easy to use these on, but they can if you use them appropriately. Okay, so we've got hardware, you've got good sensors, we've got data coming in that can be unaliased, we can control the sample rate, but if you don't have any software to support this measurement, you aren't going to be able to do very much. So previous smart sensor applications, significant effort to create very specific applications, and what we wanted to do was to develop a service-oriented architecture, one that could take the building blocks and merge them together in an application that could be constructed in a reasonable amount of time. Now, what are some of the problems? I'm going to let you guys be my sensor network. One of the issues is synchronization. If I want you guys to be my sensor network, I need you to be synchronized. The computer scientists, they did synchronization of their networks. This is an old problem, and they could get down to about 20 microseconds in synchronization. You guys are also synchronized very well with me. You can hear my voice, you can see me, and so there's a good communication connection between us. Now, the thing is although we have a good communication network, that's not the entire story. We'll conduct an experiment here. I'm going to snap my fingers, and when I snap my fingers, I want you to raise your hand. Okay, ready? 1, 2. Okay, so what you see is that there was a distribution of when people raised their hand. Some people raised their hand quickly. Some people raised their hand slowly. They were looking around, what's going on? Oh, I guess I should raise my hand. And then there were some dead sensors in the audience. There were some that didn't respond at all, and we certainly have those in our network. Sometimes they just go offline, sometimes they come back online. I hope that you all come back online for the rest of the talk. And what happens then is that you have these sensors that start at different times. So you tell them to start taking data, but they don't all start taking data at the same time. And what happens is that you get what appears to be completely different signals. There's a random phase between the signals. And if you do this 10 times, you'll get 10 random phases between your signals. So what we need to do is to be able to develop an approach that can resample this data so that they'll all be on a common time scale. And so when you take your data, then it will be useful. The data in this form is not useful at all. Now, this is really a challenging problem. Why is it a challenging problem? The typical way for handling this problem of getting things on a common time scale of resampling is that you take and you oversample the data until you get a common denominator. So until the points that you resample this data until it falls on a point of all the other sensors. So if there's just a few microseconds between the sensors, you might have to resample at 1,000,000 hertz. If you have to resample at 1,000,000 hertz, what do you do with all that data? So the approach that's taken is that we upsample the data, we filter it, and then we downsample. So we take and upsample the data, it's then filtered, and then it's downsampled again. But as I said, direct implementation that achieves the required resolution is intractable. It's just not possible. So what we did was we developed a polyphase implementation, and in the proposed approach, we did interpolation between the data points. So we upsampled, but then we interpolated so that we didn't have to upsample to such a resolution that it would not fit on the wireless sensors. So synchronized sensing was developed based on this polyphase implementation with linear interpolation as well as global timestamps. However, that still wasn't the entire problem. That worked really well in the laboratory where we were taking a minute of data and we weren't outside. However, what we found out was that the clocks were nonlinear. What that means is that the speed was a function of temperature. If it's outside, you start using the sensor, it starts heating up, and the clock speed will change. So this is the clock offset versus temperature here, and you can see that each of the sensors responds differently. So if you want to take 30 minutes of data, this is just 10 minutes of data. If you want to take 10 minutes or 30 minutes of data, you have to account for the nonlinear clock drift on top of that. And so what we developed was an approach. These are the different nodes in your network. We call them leaf nodes. This is the gateway node. And over the collection time, we send out beacon signals that can be used to synchronize each of the sensor nodes so that we've got synchronization. And typically we'll get about 50 microseconds synchronization, which ends up to be about 1 degree in phase at 100 hertz. So this is roughly what we needed. And the thing is, I show you this is because maybe you didn't understand, maybe you did understand what we were trying to do here, but you don't have to worry about it now, because this is implemented as a middleware service that you can use for collecting synchronized data that's of high quality. Another issue is, I mentioned the idea that at Berkeley, they collected all the data. They assumed that they were going to do centralized processing. And so all of the members have to report to a central station. And this is not a scalable approach if you look at, if you imagine all of the people in the United States trying to talk to the president. That's just not a tractable approach for communication in large-scale networks. So another approach that's been popular, Jerry Lynch at Michigan has done a good bit of this, and Kincho Law at Stanford, is doing independent processing. So that's where, in a society, each individual would be completely self-sufficient. You don't have doctors, you don't have lawyers, you don't have any specialization. So no sharing among data. From a structural engineering perspective, if you don't have sharing among your nodes, you can't get things like mode shapes. You lose all spatial information. So the approach that we've taken is a coordinated processing approach, a hierarchical structure where you've got layers of response, you've got groups of nodes that will do calculations and then report up to a higher level, and then there's communication back and forth. And so this also has a societal analogy where we have representative government. So this is the approach that we've taken. And I'll just show you one example of this. We call this model-based data aggregation. So the idea is that we don't want to collect all the data like they did on the Golden Gate Bridge, because it takes hours to bring that data in. So what we prefer to do is to have groups that can do calculations and extract the information. Now, one particular technique that's been very popular in structural health monitoring for ambient vibration testing is the natural excitation technique, developed at Los Alamos National Laboratory. And the main idea is that if you take the measured data and you calculate the cross-correlation function, it satisfies the homogeneous equation of motion. Now that's a result that's been known for some time in the random vibration area, but the thing that the guys at Los Alamos National Labs did was that they said, well, if we can calculate this autocorrelation function, we can then do our system identification on the autocorrelation function. You don't need to have the auto and cross-correlation function. You don't need to have the input excitation. So this is a very powerful approach. Now, to do this, to be able to calculate this autocorrelation function, to estimate that, what we typically do is we estimate the cross spectrum and the auto spectrum, but the traditional way to do that would be to bring the data from all of your remote nodes into a central node and then to calculate the cross and autocorrelations on that single node. So it means that all the data has to go to one place and you don't really get a lot in the way of economies of scale. So another approach would be instead to take node 1's data and send it out to all of the other nodes, and then you can calculate on each of the sensor nodes the cross-correlation functions or the cross-spectrum functions, and then once you have that, you can then send that back to node number 1. What's the advantage there? How many data points in a typical cross-spectrum? 1,024, 512. I mean, you're doing FFT, so you're condensing the information down. Instead of having the raw data, you're condensing it down so you just have the power spectrum that you're dealing with. And the advantage there is that we can get about a 10-to-1 reduction in the amount of data that's transferred in the network, and as a result, you reduce the power consumption. So this is an example of where we use this hierarchical structure. We use the idea that there are independent processors on each of the nodes to be able to do data reduction, feature extraction, and then eventually to move that up and use it in monitoring algorithms. Now, this is a distributed computing strategy. It uses this model-based data aggregation to do damage detection. And the idea here is that damage is a local phenomenon. If you have damage in one of the elements on this truss, it's not going to affect the response significantly far away from the response. If you have a crack in the structure, you're a couple of crack lengths away from the damage, and you go back to the free field stress. So damage is a local phenomenon, and what we imagined is that we could look at groups of sensors and do damage detection within the groups. And so this is one of the groups. We have a manager node here. All of the sensors report to this manager node. Here's a second group. You've got a second manager node, all of these sensors. So we got overlapping subgroups in our network. And we implemented this DLD method. I don't know if you've seen, it's called a damage locating vector. Dennis Burnell at Northeastern University developed this idea, and we've used it quite a bit for truss-type structures. I'll just give you the basic idea. It's really quite clever. So if you imagine that this is your structure and you've got this matrix F, it's the flexibility matrix for the structure. The U signifies the undamaged structure. So this is the undamaged flexibility matrix. Now, we've got another flexibility matrix. This is the damaged flexibility matrix, and we'll assume that there's some damage in this diagonal element. Now, where do these flexibility matrices come from? Well, they come from using some of the techniques, the next ERA method or the stochastic subspace identification, any of the popular system identification methods can yield this flexibility matrix. Now, the basic idea, though, is that you want to find a set of load vectors such that the displacement in the damaged and the undamaged structure are the same. So if you look here, F times L is the displacement, so you have that the displacement, or that the displacement in the damaged structure for a set of loads and the displacement in the undamaged structure are the same. So one can formulate this difference matrix, the difference between the damaged and the undamaged flexibility, and then we can calculate what these vectors are, L. They're in the null space of that difference matrix. Now, whoops, too far. So, what's going on there? How does this work? So I calculate the flexibility matrix using system identification techniques. I've got a baseline, and then periodically I come back and I calculate it again, and I calculate these load vectors. Now when I take, what's the only, or not the only way, what is the main idea if I have that I apply a load to this structure and I apply a load to this structure which has damage in it, and I get the same displacements? How is that possible? It must mean that the load path in the structure doesn't go through this element. So if in the undamaged structure there's no load carried by this element, when you look at the damaged structure, if there's no load carried by this element, the displacements will be the same in both cases. So the process goes from a calculations perspective. I calculate these load vectors that are in the null space of this difference matrix, and then I apply them to a model of my structure, and I look for elements that have low stress. And those are the candidate damage elements. So this type of thing, this type of an approach we implemented, and we looked at it in this distributed computing approach to see if we just measured the sensor locations in the vicinity of the damage, could we detect the damage? And this is the stress in the element. This is the stress in the sensor, in the element associated with a given sensor group. And so what you see, this is associated for this element, and we find damage here in element number 5. You can see element number 5 has small stress. We do this again for the second group, but there's no damage. Element number 5 is right here, it's that diagonal, and so it's not in this sensor group, so we don't have any damage found. So the DCS logic, we've got cluster heads, inquire the neighbors about the identified damage. So these sensors will talk to each other. They will say, oh, I've got damage, or I don't have damage, and then those nodes will communicate with each other to see if there's consistency in the data. This logic was all built into this iMote2 by Tomonori Nagayama. We had some reference sensors on here so that we could ensure that the data being collected was accurate. And so the system architecture, homogeneous hardware configuration, functionally differentiated, that is, you had manager nodes, cluster heads, leaf nodes, so we had this distributed computing strategy implemented. This hierarchical network was implemented on the network, and the smart sensors could change their roles depending upon the configuration needed, so they were task-based. And this is the experimental verification, where we had an element that was damaged. We had the PC collecting the data from the various nodes. The results were numerical identical to those on the PC, so we were able to confirm the calculations on the wireless sensor nodes. And then we took 10 iMote2s in 3 clusters to autonomously monitor the 3D scale truss. These were the 10 nodes. Whoops. These were the 10 nodes. There's group 1, there's group 2, and there's group 3. And we had a reduction in cross-section of this element. And what you can see is that this is using the stochastic DLV method. It was able to identify damage in element number 8 in groups 1 and 2. Element number 8 wasn't in group 3, so there was no damage. So the manager nodes between these two groups would talk. This fellow would say, hey, I found damage in node 8, in element 8. And this guy would say, yeah, I found damage in element 8, and then that would be reported back to the base station. This is just looking to see if we had damaged elements at different locations, as well as vertical elements and diagonal elements. How effective was the damage detection? And so experiments were repeated 3 times for each case, and what you can see is that this is damage in element 8, sensor community 1, 2, and 3. We got good damage characteristics. So false negative, 0 out of 6. Sometimes you do get false negative or even false positive damage detection, but in this example we didn't. Now this is just the one particular example, but once you decide that you want to implement this on a full-scale structure, you have to worry about all sorts of things. In the laboratory, we didn't have to worry about energy harvesting. We didn't have to worry about putting the sensor to sleep to conserve battery performance. And so all of this is just a couple of examples of the damage detection strategies that are implemented. We've actually ported the entire LAPACK library to this wireless sensor platform. So there's singular value decomposition, eigenvalues, solutions of Lyapunov equations, etc. And all of this is implemented in the wireless sensor suite. But I just wanted to, the first student, Tomonori Nagayama, he had 207 files to implement this damage detection strategy that I just showed you, 8,000 lines of code in the core application, and for the numerical subfunctions, 54,000 lines of code. That was for porting the LAPACK library. So it was a huge investment. Now, I asked him, I said, Tomo, how long would it take you to, for the next student to learn about this? And he said, oh, probably about a year. Take a year to learn about the coding before you could actually start doing research. So we didn't feel that was reasonable, and we worked, so this slide was that last slide was out of place. So we worked with colleagues in computer science to develop what we call the Illinois Structural Health Monitoring Services Tool Suite, which takes all of these things and puts them into a framework that can be used, an open source framework. This is the IHSMP tool suite. It's got the foundation services, the network services, the application services, the testing services, and it provides that middleware interface between the application and then this low-level operating system and the hardware. They're available on our website at this link. So now I'd like to show you 2 full-scale deployments. We've got the hardware, we got the software, we demonstrated it in the laboratory, but then when we went out onto the bridge in the full-scale implementation, we found a lot of challenges. So this is the Jindo bridge. This was a joint effort between KAIST and Seoul National University, the University of Illinois, and the University of Tokyo, Professor Fujino and Nagayama. This is a twin bridge. It's located between the Jindo Island at the southern tip of the Korean peninsula and the peninsula itself. And so you can see there's 2 bridges here. This was an older bridge that they built whenever this was a sleepy island, and then they put a shipyard over here, and the traffic very quickly outgrew the capacity of the bridge, so they put in the second Jindo bridge, and this was the target of our first study. 344 meter center span from tower to tower. And we had our first deployment in 2009. We put 70 nodes on the bridge. Why did we put 70 nodes on the bridge? If David were here, he might know. It's because Berkeley did 64 and we wanted to get just a little bit above Berkeley. And so we put 70 nodes on the bridge.
They had like 128 accelerometers.
So we had 640, so but it was the number of nodes, so that's how many wireless computers you have, etc. So they had 64 nodes, and they had 2 accelerometers and 1 temperature sensor. So in each of our nodes we had 3 accelerometers, and we had a temperature, humidity, and light sensor. So we, I don't know about better, but there's always a friendly competition between the 2 civil engineering programs. This shows you how some of the nodes were deployed. We had them on the cables, we had them on the bridge deck, they were on the towers. We had a wireless anemometer that was installed. And so 420 channels, 207 of acceleration, and 3 of wind. In 2010, You see, the problem with that wireless sensor node was it worked for about 3 months and then it died. Because we just had batteries in there. We had D-cell batteries, and so it was great for a test bed, but we felt that it didn't really show the potential of the wireless sensor. So in 2010, we went back and we put sensors on all of the cables. You can see now they have solar panels. There's the little antenna. This was the complete unit. We went up, we attached it to the cable, and it self-configured and started working. This is on the tower. You can see the wireless sensor held on by magnets. In this case, that's the wireless sensor right there. This was the base station. It was on at one of the pylons, and it was an industrial-grade PC. There was a UPS in there. This is one of the sensors that was on the pylon. This was, we did some investigation of some micro wind turbines for energy harvesting. This was the wireless anemometer. We had 3 wireless anemometers put on the bridge to characterize the wind field. And this was one of my students, Hongi Joe, and you can see the magnets attaching the wireless sensors to the bridge deck. So we didn't have to do any cleaning of the paint or glue or the like. They were held on strictly by the magnets. This was one of the solar panels that was on the side of the bridge. And this was the interface where we could access the data from any place in the world. So this shows the deployment. We had a total of 113 nodes on all the cables. This shows where the cables network was. This is the bridge network, and this shows the types of sensors we had for temperature, for strain sensors, for high sensitivity as well as regular sensitivity accelerometers. And this just shows the various networks. Now, I don't expect you to get much from this other than just to tell you that it was a test bed. We tried different functionalities. We had different temperature capabilities. We had different types of sensors. We had different communication protocols from single hop to multi-hop communication protocols. So a multi-hop communication is where you've got nodes, they're too far from each other to talk to the base station, so they'll just hop, sending information back to the base station. So 669 sensors in sensing channels on 113 sensor nodes. Now, as soon as we got done, Typhoon Kampasu came through near Jindo. This was some of the damage of the typhoon. What you can see here is the Jindo bridge, and then this was the center of the typhoon. This is the path of the typhoon. Here's the bridge, and you can see on September 1st it was the closest to the Jindo bridge, Jindo Island. It gave us a great chance to figure out if our system was performing effectively. So, this is the wireless anemometer that was attached to the bridge, one of 3. And it just so happened that there was a meteorological station. Here's where the bridge is, right here. So there was a meteorological station on the mountain that was on the Jindo Island. And these were the recorded behaviors. So the wind speed is shown here, wind direction is shown here with this arrow, and the wind speed was 15 to 20 meters per second. Now, if you look at the bridge, this is a blow-up of the bridge here. What happened was that the wind direction changed because this is a narrow strait, and so it funneled the wind over the bridge so it was perpendicular. And it also increased the speed of the bridge. These are 2 of the 3 anemometers. And what you see is that the wind speed is in the 20 to 25 meter per second range, some almost up to 30. So it increased the speed and it slightly changed the direction as it was going through this narrow strait. So that gave us confidence that our wind measurements were effective. Now, these are some of the accelerations that we measured. Now, I showed you this DLV method before that we implemented for the truss structure. But this is not a truss structure. So what's important for this type of a structure? Well, many times, and let me just say that, do you see here, this is the power spectrum of the response. And do you see, how could you say that there's nothing above, say, 4 hertz? There's data all the way up to 100 hertz. So you have to have these anti-aliasing filters. If you don't have filters that cut off the energy in the system, you're going to have aliasing in your data. Now, structural health monitoring. Many people make analogies between human health and bridge health or building health or infrastructure health. And I don't think that's a very good analogy. You know, they may say, well, you've got a physician and they're examining the patient, and so that the infrastructure that we have are the patients in our society. But I would beg to differ. And the example I would give you is that the measured temperature, if it's 101, what would be the diagnosis? You say, well, the fellow has a fever, right? Well, what if it was a llama? The diagnosis would be normal. But what if the measured temperature was 92 degrees Fahrenheit? Well, you'd say that llama is in hypothermia. It's not a good sign. But if it were an iguana, you'd say, oh, that's normal. So I make this analogy because I think a veterinarian is a much closer analogy for structural health monitoring than it is a physician. Why? Humans are basically all the same. But our infrastructure is not all the same. This DLV method that I showed you works very well for truss structures. But it doesn't work at all for a cable-stayed bridge. It's not an important measure of the behavior of that cable-stayed bridge. And so if you want to look at a cable-stayed bridge, you have to find out what's important for that cable-stayed bridge in the same way that if you were going to look at an iguana or a llama or a parrot, you'd have to know what was appropriate for that. So for the iguana, 101 or 92, it could all be normal because their body temperature, they're reptiles, and so it can adjust. So in structural health monitoring, the expected behavior of the structure needs to be known in order to determine the meaning of the collected data. So a lot of the things, this Vincenzo talked about yesterday with model updating. You have to have a model of your structure so you can understand what's the expected behavior. If the behavior of the structure is unknown, then probably you're not going to be able to understand your data very effectively. So one of the first things that one will do is to develop a model. On the right-hand side is a model of this Jindo bridge. On the left-hand side is the mode shapes that were estimated based on this next ERA method, so the natural excitation method that I mentioned to you before. And we did some things with decentralized modal analysis that would allow us to get these behaviors without collecting all the data. And what you see, this was in 2007 a wired system. This was our finite element analysis. And this was the collected data during the typhoon. And what you see is that even for these higher frequency modes, the modal survey of the wired system and the wireless system, this was not during a typhoon. The frequencies are quite consistent. And they're also quite consistent with our model. So what does that tell you? That says that even though this typhoon came through, it really wasn't a big event for this particular bridge. We're still in the linear range with the response by and large. We still have very clear mode shapes. And so this typhoon was not a challenge for this bridge to undergo. So what's important for a cable-stayed bridge? It's the tension in the cables. If you have, the cables are like the strings in a guitar. So if you have the strings in your guitar are tuned inappropriately, it can cause deformation in the guitar. It can even cause warpage and serious problems. So if you have the tension in your cables are not within the design range, then this can be very detrimental to your bridge. The tension in the cables can change due to corrosion, due to collision with automobiles. Actually, we almost got in trouble. I don't have the picture of this. One of the students, we had a sensor. We had one of those dead sensors that I talked about earlier. The solar panel had failed, and so the battery, a lithium polymer battery, inside of the box had died. Now, we needed to either replace or recharge that battery. Now, we'd put the batteries in the box with Velcro tape. Seemed like a good idea at the time. And so the student went to the box and he grabbed the battery and he started pulling. Well, if you noted, that battery was very thin. It was about this big and about this thin. And so he started pulling on it and it bent. And it started combusting. It started a big fire right on the cable because he had bent the battery. So when people say that lithium polymer batteries can be dangerous, they're not joking. So we almost got kicked off of the bridge because we started a fire on one of the cables. If you start a fire on the cable, it damages the sheathing, you can get moisture in. Nothing good can come out of that. But fortunately, it didn't cause a serious problem, and we were able to continue. And what you have here, these are the cable tensions estimated in real time in red for cables 1 to 12. You can see that compared to the design tensions, they're very reasonable. And this was an analysis that was done by Park in 2008. And so you can see the estimates that we achieved by looking at a vibration-based approach, looking at the frequencies of the cable. They're within a few percent. And in actuality, each of these cables were not just a simply supported cable, like a pin-pin cable, because they had dampers on them. You remember the galloping vibration problem that I talked about yesterday for these long-span cables? This bridge had a serious problem. So they put dampers, lead rubber dampers, penguin dampers from New Zealand on those cables. And so given that the bridge had changed from 2007 and 8 until 2010 because of the cables being, the dampers being put in, and that there was a nonlinear character there, being within a few percent is quite appropriate. And then if you track that over time, if you saw any significant differences, you would know that. So this is like the damage measure for cable-stayed bridges. This is like measuring the temperature of the iguana. It's not the DLV method. This is just show some strain data that we took. These strain gauges were mounted inside of the pylon because they didn't want us to grind the paint on the outside of the pylon. What you have here is the acceleration time history. Over here is the strain time history. Now, what we thought was really interesting is that in the acceleration history, there's nothing below 2 hertz. It's just, there wasn't anything in that signal. But if you look at the strain history, you can see that it's very rich below 2 hertz. You've got this 2.4 hertz pylon bending, but these are all interaction between the pylon and the bridge deck that weren't seen in the accelerations. So what that shows you is that a multi-metric approach to structural health monitoring can be very important. The accelerations may give you information about the global behavior, but the strains may tell you more about the low frequency as well as the local behavior. Now, I'll show you something interesting. Probably in structural mechanics, you've all studied influence lines. And so we put 2 strain gauges. This was that magnetic strain checker that you just attached with a magnet, and then you ran the wires to your wireless sensor. So we put one here to measure the strain on the bottom of the bridge deck at the pylon and at the midspan. And this was the behavior that we got. Rather strange. This is the pylon at the pylon bearing, and there's this double peak. Sometimes the small peak comes first and then the big peak, as was shown here, and sometimes the big peak comes first followed by a small peak. In the center span, it was a little different. There was usually a single peak here. This was due to a big truck going across, and it caused the magnetic strain checker to slip. But at the center span, you have these single peaks. At the pylon, you have double peaks. And so why do we have these double peaks? We did a finite element analysis using this truck, a 12-ton truck, going across at 60 kilometers per hour. And we looked at the center span and we looked at the pylon. And what we found, these are the influence lines for a truck driving northbound over the bridge. This is for a truck driving northbound over the bridge, the influence line for the strain at the midspan. And what you see is that these influence lines show exactly the behavior that the data shows. Moreover, if you measure the distance between these peaks, you can find that you can estimate the speed of the truck going across the bridge. 3.1 seconds here, 51 meters, and so that gave 60 miles per hour. If you then calibrated your strain measurements, then you'd be able to you'd have a complete weigh-in motion system where you'd be able to get the speed and the loading of the trucks. This single peak at the center span, what you see in the data is that meant that there were 2 trucks going over that bridge at the same time near the center span, and so it ended up, it showed as a double peak. And they had roughly the same weight, so maybe this is a couple of cars, this is a larger truck, this is again as a car. And so you can understand the basic traffic patterns by these strain measurements. In addition to monitoring the response of the structure, this is an example where you can monitor the battery performance, the charging of the battery. Here we have the charging current, here you have the battery voltage. And what you can see is that on a sunny day we have higher charging current. At night there's no charging. And on a rainy day the charging is less. This is a double slide, got in there somehow, we'll skip that. Now, what you see here, and this is what I had mentioned about having some dead sensors. For whatever reason, you've got a base station and it can go down. We need to do more work with regard to the reliability of the network, but you can see there were times when the network was not responsive. Here, this was due to problems on the base station where these blue lines are, where the data just wasn't collected. But by and large, we got the response of about 70 to 85% of the sensors at any one point in time. So what were the achievements? We had hardware achievements in terms of the number of nodes, the types of nodes, high sensitivity accelerometers, solar panels, wind-induced harvesters. In terms of the analysis methods, we did modal analysis with system synchronization, vibration-based tension estimation, multi-scale structural health monitoring, wind vibration correlation analysis. In terms of the software, we developed fault-tolerant operation, multi-hop reliable data transfer, remote software updates. And all of this, I think, was driven by this international collaboration that we developed. It moved forward much faster than we would have done otherwise. And so this is still the world's largest deployment to date of wireless sensors for civil infrastructure monitoring, and it's the world's first long-term deployment. Now I'll show you a second deployment. This is maybe interesting because it involves the monitoring and management of railroad assets, and it's if we look at what I had said about fatigue, this is a particularly challenging problem because up to 90% of the fatigue life is spent in crack initiation. We don't even see the cracks. Visual inspection is the standard, as well as using strain measurements. But you have to have the measurement of the strain very close to the potential damage location. So offshore structures, in addition, getting to the locations where cracks may be occurring, where fatigue is a problem, is a very challenging task. Here are some other examples of fatigue. This is crack in the wing. This is where the fuselage was damaged. If you guys remember this 1988 flight to Hawaii. This is that I-bar that I mentioned on the Bay Bridge. In the 2007 inspection, there were no problems. In the 2009 inspection, the crack had already grown to failure. This is just an indication that 90% of that fatigue life is spent in crack initiation. Fracture critical members, the typical ways we'll use a finite element model, design loadings, but they can't represent the real condition. They can't represent the traffic patterns. They can't represent fault selection of critical members or monitoring of unmeasured members. So there's all sorts of challenges in doing fatigue monitoring of structures. So in this project, we developed a novel approach. It was based on some work. Papadimitriou had originally had the idea fellow in Greece. And what we wanted to do was to figure out a way that we could determine the fatigue life of arbitrary members that weren't measured by your monitoring system. So the basic idea, we're looking at this model-based approach. We're combining physical monitoring with numerical models. So you imagine that you've got physical measurements on several of the elements, but you don't have them on all of the elements in your structure. You've got a numerical model that's relatively accurate. It's done from the updating. And then one can use Kalman filtering to use the measured response to determine the response at unmeasured locations. And so with this Kalman filtering approach, I can get the estimates of the response for all the members in my structure. Now this just shows the approach that was taken, a state space approach where we assume that the output are the displacements of velocities and the accelerations. And we assume that we've got a filtered white noise. So we use an shaping of the input excitation. In a Kalman filter, you typically assume that the disturbance is a white noise. But we will use some filter to shape the spectrum. And then we create an augmented system on which to do the estimation. Once we have that augmented system, we can then estimate the states. We can solve the algebraic Riccati equation. We assume we've got stationary responses. And then we can use those output responses to feed in the Palmgren-Minor rule. We can use SN curves and rainflow counting. Actually, Downing and Sosi are both at Illinois, and he was on one of the members of the research team for this student, research committee for this student. So from the estimates obtained from the Kalman filter, we can estimate the fatigue life. And so with that estimates of the fatigue life, using the measured data, then arbitrary locations on the structure can be monitored. So I have a numerical example here to show you in the last few minutes. This is that same 14-bay truss. We assumed several configurations. In the first case, we had 2 strain measurements. In the second case, we had 4 strain measurements. In the third case, we had 4 acceleration measurements. And in the fourth case, 2 strain and 2 acceleration. So we get to this multi-metric approach for damage detection here. We assumed 5% error in the model. We assumed that the measurement noise, 70 microGs per square root of hertz, 10 microstrain per square root of hertz. And then what we wanted to do was to look at the possibility of estimating the strain here at an unmeasured location. So this is the result. If you have 2 strain gauges, these are the time histories. They look pretty good. It captures the low frequencies very well. We said strain, give us a good picture of the low frequency behavior. But at the high frequencies, and you can have a lot of cycles going on at the high frequencies, the strain doesn't do a very good job of giving us the response of the structure. Here is the error at element number 9. It's 4 microstrain RMS, plus or minus 10 microstrain in terms of amplitude. Not that accurate for the high frequency range. If we add 2 more strains, we reduce the error. It gets down to about half, but we still don't have very good characterization at the high frequencies. But you can see just in the time domain it looks really good, but at the high frequencies we still have substantial errors. Better than case 1, but let's look if we add 4 accelerations. Now, if you look here, now we get very good performance in the high frequencies. We get reasonable performance in the low frequencies. But if you look, there's this low frequency, due to the error right there, there's this low frequency error. And the RMS error is 9.7 microstrain. So you've got the accelerations alone don't do a very good job. The strains alone, they do okay. But the merit is in combining them, this multi-metric approach. What you see is 2 strains and 2 accelerations, still a total of 4 sensors. We get good characterization in the low frequency, good characterization in the high frequency, and the RMS error in the unmeasured element is down to less than 1 microstrain. If If you then turn to the fatigue life estimation, this is the truss elements, so we can determine the fatigue life in all of the truss elements, not just in the truss element 9 or in the ones that we measured. And what you see here, if we look at this detail for the top chord, is the reference that's without noise, so that would be the exact result. So the black circle is the exact result. And so the Kalman filter estimates using the multimetric approach gives our best results, but the 4 accelerations don't do too badly. And why is that? That's because at the higher frequencies, that's where a lot of the fatigue damage goes on, not necessarily at the lower frequency responses. So just 2 strain gauges really underestimates the fatigue life, and the even with 4 strain gauges, because it doesn't capture that high frequency, it just doesn't do a very good job. So this is just an overview of the approach that's been embedded in the wireless sensors. And so the hardware and software support for high quality multimetric measurements is essential for the success. So we've got the wireless strain gauges, magnetic strain gauges, we've got the onboard processing, and so it's a very effective system. And this is the test bed. We haven't got full implementation here, but we've started. This is really a neat structure. It's a double deck. On the lower deck is highway travel, and on the top is rail travel, but it was built in 1896. Now for Italy, that's still probably a new bridge, but for the U.S., that's a really old bridge. And it's unique because it's a swing bridge. This is over the Mississippi River, and so that bridge swings to allow barge traffic to come through. So if you imagine over 100 years ago, they had the mechanical expertise to be able to swing this large bridge as shown here. So we used the IMO2 sensor enclosure as I showed you before. I should have pointed out that when that typhoon came through on the Jindo bridge, we didn't lose a single sensor. These magnets are really impressive, and they're low cost too. This is the wireless sensor installed on the bridge. This was one of our technicians up on the top of the bridge deploying the sensors. And so the goal here is adaptive wireless sensors for automated finite element updating, automated load estimation, and automated fatigue damage estimates. So that's where we're going. Now to close out, I think you'll all find this interesting. The question you may have is, what do fish have to do with structural health monitoring? There's a lot of work of late in what is called bio-inspired mechanics, bio-inspired engineering. And so there's a fellow at Illinois that works with smart fish. And I think there's a lot that we can learn from smart fish. So first, my colleague is Mark Nelson, and he's looked at sensing strategies for these electric fish. Now the way that these electric fish work is that they send out a weak electric field, and they have sensors along their body that can measure the electric field, and if they see any disturbance in that electric field, then that will be noted. Now this is what's really amazing. You know, I talked about one of the problems that we have as engineers is data inundation. There's just too much data. This electric fish has 15,000 sensors. That's really the goal of what I'd like to have. I'd like to have my sensors to be so low cost and so effective that I can put them everywhere. I could have 15,000 sensors on my bridge. One nerve fiber, that is one of these individual sensors, has up to 1,000 temporal pulses. So it's going at 1,000 hertz. That means it's generating 15 megabits of data per second. That's data inundation. Now, if you might imagine, that fish has a really small CPU. The brain of that fish is small. So how can it process all this data? How can it make use of it? Well, it's even more perplexing because with those 15,000 sensors, this is what the fish sees. That would be the equivalent if you had some prey or some food. It sees a fairly low quality image. So you don't need 15,000 pixels to be able to represent that image. So why is the sensor density so high? And that's amazing. So the facts, the individual electrosensory sensors are relatively low-resolution devices. They do not provide reliable event detection, and they're easy to replicate. So what that means to me is that if I can figure out how this fish does this, then I can use cheap sensors on my structure and still get high-quality data. So what the nervous system does is it creates virtual sensors with the desired resolution and sensitivity using this data. How does it do that? Well, this is the fish's brain, and these are the different maps that are in the brain. So the sensors are broken up into different groups. In this, let's see, in the CMS map, we've got very high spatial resolution. In this LS map, I've got very low spatial resolution. So what will happen is the fish will group a bunch of those sensors together, and it will create these different mappings in the brain. So this, again, that's grouping a bunch of sensors together. This is just looking at very few sensors all at one time. Now, how does it take these different mappings and put them together? Well, this just tells you the problem that we've got. So skin sensors, 15,000. In this CMS mapping, there's about 40 sensors per node. And so in the brain, there's about 2,800 discrete points that it can figure out what's going on. For this CLS mapping, there's about 200 sensors per node, so there's about 1,400 sensors or discrete points in the brain. And for the LS map, there's 900 discrete points in the brain, and each of them corresponds to about 1,000 sensors. So how does it use that? Well, this centroidal map, centromedial map, where you have high spatial acuity but low temporal acuity. What does that mean? That means I know exactly where that point is, but I don't know when it's there. On the other hand, in the lateral map, I've got low spatial acuity. I don't know where it is, but I know when it's there. And so by using this type of temporal integration, spatial integration, and intertemporal integration, the fish is able to, this is food, this is a top view of the fish, this is a side view of the fish. And let's see if we're going to, whoops. This should be a video. I guess it's not. Somehow that video didn't get included. What we would have seen here, let's try that again. Nope, I guess the video somehow didn't get included. What you would have seen is that the fish swims by and then it backs up and it eats the food. So by using this temporal and spatial processing, it can capture the prey. So the nervous system implements these virtual array of smart sensors using dense, cheap, low-resolution electroreceptors. And so these are smart sensing strategies including multi-scale filtering, task-dependent filtering, and subtraction of sensory expectation. That means you have to know your model, you have to know your structure to be able to implement some of these strategies. So we've been doing a lot of work in this particular area, working with Mark Nelson to be able to develop new strategies. They're still in the oven. We haven't got any baked yet. But I hope to have more to tell you about this in the future. Now, a lot of what I've told you about today may seem to be pretty far from mathematics, engineering, mechanical, civil engineering, and indeed, what I discussed yesterday, what I discussed today, it's not in the standard curriculum at most universities. And so, partnering with colleagues in Korea and Japan and China, as well as Taiwan and India, we've developed the Asia Pacific Summer School on Smart Structures Technology, and it's a 3-week program that's supported by the National Science Foundation in the U.S. And we've had these programs starting in 2008 in KAIST, and then moving on to Illinois, Tokyo, Tongji University, Bangalore, back to KAIST, and next year it's going to be at NTU, National Taiwan University. And so if you have any interest in this type of the types of things I've spoken about for the last couple of days, then this would be a great opportunity next year to participate in this summer school. They have competitions, so you do the lectures, you do laboratories, and then this was a competition to do system identification on this pedestrian footbridge. This was at Illinois. This was a site visit in either Japan or Korea. So it's a really exciting program. So in conclusion, recent advances and field validations of the state-of-the-art wireless sensor network we developed at Illinois, I hope, have been laid out during this presentation. We've shown some of the full-scale deployments that were realized using this particular approach. I also talked about a model-based fatigue monitoring. This is just one particular example of an algorithm that could be deployed. And then at the end, I said, we have to think about the education of the next generation of engineers, because this is very multidisciplinary, interdisciplinary, and so we need to start thinking about new educational paradigms to allow us to make headway in this research frontier. So these are some of the students that worked on this, as well as some of the funding for the project. So thank you very much, and if you have any questions, I'd be glad to answer them.